Hello everyone, welcome to this lecture of a simplified hybrid pi model of a BJT. We'll try to understand how to form an equivalent circuit of a transistor, and we'll also try to derive the equations regarding that circuit. Before diving into the details, we need to know some basic knowledge of transistors, DC biasing and analysis of a transistor, some basic circuit analysis like KVL and KCL, and some network theorems. So let's start. This is a very basic diagram of a single stage BJT based or transistor based amplifier. The main goal of this amplifier is to amplify this small input signal here by a very large amount. So this input signal will be collected at the output terminal. So we want this signal to be very large. This is our main goal. Okay. So first we'll need to know some terminologies regarding this transistor circuit. So where every term is in capital letters will be denoted as a DC term. So this is a DC term. This is also a DC term. Let me change the color. This is also a DC term. Okay. And where everything in the small letter like this VBE, this will be regarded as an AC signal. And where the letter is capital and small mixed, these signals will be denoted as both AC and DC terms. So this is a mixture of or summation of AC and DC terms. Okay, so the first thing to notice is that this is an NPN transistor. Okay, and we have two DC sources, this and this, and the main role of these DC sources are to take this transistor to an active region, because we're trying to amplify a signal, so we're trying to use this transistor as an amplifier. For that we have to bias this transistor in active region. So this is the main role that this DC signals play. Okay, so you already know from superposition that each signal or each value of this circuit will have two components, one a DC component, another one is AC component. So for example, if we apply a KVL in this loop, we can easily determine the VBE, which will be a summation of this AC signal, small signal, and this DC bias signal VBE. So similarly, we can determine the IB, which will be a combination of a small current at small signal or at AC analysis and a DC current. So for IC and IC, the method is similar. Okay, so our goal in this lecture will be to determine the equivalent circuit of the transistor for these AC signals, these small signals. We will not bother about these DC signals because we already have done DC analysis. So this is not our concern for this lecture. Okay, so let's move on. I hope everything is clear up to this point, because this is very basic analysis. Okay, so this is a DC analysis. We'll give a small recap. So in DC analysis, we have shorted out this AC term or AC voltage source, and we have only IB, IE, and IC, and two voltage sources here. Okay, so the equations we already know because we have already covered this topic in the previous lecture. The IC current is IS to the power VBE by VT. This VBE is the base emitter voltage, and this VT is the thermal voltage, which is equal to 26 millivolt. It's close to 26 millivolt at room temperature. And we also know this equation very well. IC is equal to beta into base current, collector current, and emitter current is collector current divided by alpha. Okay, let's move on. So now we'll try to derive the equations at AC signal. For that, we already saw that each signal will be a combination of AC and DC terms. So we already know the analysis and equations of these DC terms. We'll just need to find out the equations regarding these AC terms. Okay, this is a very simple circuit, and we'll just use KVL KCL. That's all we know. For example, like in this loop, we can say that the VB is VBE, small v and capital B is equal to V small b, the small signal or AC signal, plus V capital BE. This is the DC analysis. Okay. Now, if you want to calculate the IC current or collector current, then IC we'll use this equation just for this case. So IC, small I and capital C will be IS, saturation current, to the power V small v capital B by VT. I think everything is clear up to this point. This is very simple. We're just using this diode current equation here. Okay. Now we'll have to replace this V by this term. Okay. Now let's do that. Is equal to will be e to the power V small ve plus V capital Ve divided by Vt. Excuse my writing. Okay. Now Is will be if we expand this, e to the power Vbe by Vt into e to the power V capital Ve by Vt. Now, if you look closely, this term we have already studied in the DC analysis. This is exactly this term. So this becomes the DC collector current. Okay, so we can write it in this manner, that IC, the DC collector current, to the power VBE by VT. I think this is very easy to understand. Now we'll try to use a binomial approximation of e to the power VBE by VT. So which will be IC 1 plus VBE by VT. Okay, now we'll try to expand this a bit further. So IC, this IC will be equal to IC plus IC VBE by VT. I think this is very easy to understand. So now if we compare this result with our initial slide, look here, IC is equal to a DC component plus an AC component. So we already have this IC in our this equation. So we can all easily say that this is our AC current of the circuit. So we can write that I small c will be equal to IC VBE by VT. I think this is clear up to this point. So using superposition, we can easily determine the AC component of our total collector current. Okay, so we'll keep this in mind because we'll use this equation further. Okay, so we can, if we look closely, we can see that IC by VT, this can be modeled as a transconductance gain, TNC. So we'll denote this term by GM. So now if you write the equation of IC, it will be IC. Again, reminder is that this IC is only the AC component of this total IC. I think I'm clear because we have already shown the equation in the first slide. Okay, so this will be equal to GMVB. So we have already found out the collector current at AC analysis. So yeah, bingo, we have done something all right. Okay, so now we have to find out the base current and the emitter current. So then we'll be done with our work. Okay, so let's move on to the base current section. So IB will be similar. I large B, that means the AC and DC component at along. This will be basically I large C divided by beta. Then we have already determined the equation of I large C, I capital C. So this will be IC plus IC B small be divided by Vt divided by beta. This will also be divided by beta. Fine. So you can see that this is nothing else but the base current at DC. This is very easy to understand, I hope. And this is also another GM, the same GM we have derived or shown here. Okay, transconductance gain. So we can write that GM by beta VBE. So this portion is the DC term, and this portion will represent the AC base current at small signal. So this will be small I, small b. So we have found out the small ib also, and from this we can also determine another thing, which is very interesting. We can see that ib is equal to gm by beta vb be small b. So here you can see that this is also the small signal, this is also small signal. So in this equation, everything is in small signal mode. So we can model this using our ohm equation, like the ohm equation. So what ohm equation says, V is equal to IR is the ohm equation. So we'll model this equation like the ohm equation. Then we'll get that V is equal to IB beta by GM. This will represent as an resistor if we compare this to the ohm equation. So this resistor is basically called the R pi resistor. So we have also found out the R pi, which will be beta by GM. So let's just recap what we have done. We have found out the collector current at small signal. So when this is not active, we also found out the base current at small signal. That means this is not active. So we just need to find out the IE. This is the select. So we can do this later also, but let's try to draw the equivalent circuit if we are able to do it. Okay. So now at small signal, what will be the case? At small signal analysis. Okay. So at small signal, we'll short out the VDC. So this will only be V small b, and this will be our transistor. And this VDC will be also shorted out. So there is nothing. And there is a RC collector resistor. Okay, fine. So we'll have small I small b, we'll have small I small e, and we'll have small I small c. Fine. So we're almost there. We just need to yeah, I think we're almost there. Okay. So we already know the IB, we already know the IC, and we just need to know the IE. We also know that the voltage between this base and emitter terminal is VB. So we can easily model this base emitter terminal. So first let's do this, and then we'll move on to the next section. So what we have know already, that IB is equal to VBE by R pi. Okay, because we have already seen this equation here, or for example this equation, this is both the same equations. Okay, so you can see that we have already modeled these two terminals as an equivalent small circuits. So we can just write this circuit or draw this circuit, that my IB comes here. Okay, it goes through R pi and it goes through the emitter terminal. So this is my emitter terminal, this is my base terminal, and this is the V small b base emitter voltage. We can see that this is the exact model. which you have here. So this equation represents this model. So we have already done half of our job. We have already converted this base emitter junction to an equivalent circuit. Uh, all left is that we need to convert this emitter collector junction also to an equivalent circuit, which can be also done very easily because we have already seen that that IC is nothing but just a current voltage control current, and this voltage control is current is controlled by the voltage of the base emitter junction at small signal by gain. This is the transconductance gain. So we can easily replace this IC or model this IC using an voltage control current source. Okay, so how can we do this? This will be denoted as GMVBE. I think I'm clear. Okay. So to summarize our discussion, what we have done is we have taken an NPN transistor, a BJT, and we have derived the equivalent circuit, the hybrid pi model. So this is the hybrid simplified pi model. Thank you for staying with us.